Hey everybody. I guess we're having a snow day tomorrow. Uh, so I'm recording a video so that we don't have to worry about a Zoom class, of course. If you're watching this, you've probably read the announcement, so I guess this is redundant. Um, I also found free use footage of Subway Surfers to emulate the TikTok videos to help with all of our attention spans. Uh, so I have Subway Surfers playing in the corner. So I know it's a guarantee that I'm holding on to everyone's attention. I put way too much effort into getting this like this. Okay. So I actually developed a few what you would call like, I don't know, interactive things that I was gonna do in class, but this works just as well. So we're gonna go through these examples to get our lesson out. So first, I actually want to start by reminding us what the graph of sine looks like. So this was something that we touched on Monday, but yeah, this is saying our angles in radians are going to be our input, and the height, the y value on the unit circle, aka sine, is going to be the output. So here we see that uh, at 2 pi, about 6.28, we complete our first period. So again, sine starts at 0, and then once we hit pi over 2, sine is 1, and then we go back down to 0 at pi, we go to negative 1, and then we go back to 0. So again, just this basic sine graph. Now, this comes from looking at the unit circle and taking inputs as angles and outputs to be the y value, aka sine, right? So this is just the basic graph of sine. And again, I said that we keep going to the right, and we're going to keep going with the same shape forever and ever and ever. And the same thing is true going to the left. We're just going to copy and paste sine forever and ever and ever. Okay, so from 0 to 2 pi is that first period right here, but really sine exists for all numbers x that I can plug in, and it just keeps going in the squiggly line like this. So that's the basic graph of sine, right? From 0 to 2 pi right here. Okay, so this notebook that I made, we're going to look at this kind of word problem and see what happens there. So let's consider a broken clock with the minute hand being 1 foot long all the way to the edge. Now let's say it's moving counterclockwise and is starting with the minute hand flat at 15 minutes. All of that weird situation just to say, pretend our unit circle is a clock that starts where the unit circle normally starts, with the angle 0 being in centered position, just flat like that. And then let's say that our clock starts to move the same way that our angle starts to move by going counterclockwise. Let's graph the vertical movement of the minute hand through the hour, aka let's graph the height of the minute hand in this situation, which is the y value, which is sine. So right here, what I'm about to do, we're just going to increase our angle. Right now we're starting at 0, and as the angle increases, we're going to draw the graph of sine. Now you're going to notice some weird red shape happening in the background. Please ignore that for the most part. Mathematica is a weird program. Okay, so our angle is going to start increasing, and we see this line that we're making, right? Our line is going up, our minute hand is ticking counterclockwise. We're getting this angle here, and that angle is the input, and the height of the clock is the output of the function that we're graphing. So genuinely just notice the height of the circle is perfectly matching, right? The height of the point that we're graphing. So as we continue, we trace out our sine function by taking these angles as the x value and the y value as the output, right? All I'm doing is saying a bunch of different ways that we're just graphing sine right here. Okay? And this is pretty neat, right? I can hit play and it's just going to draw this. This is sine. We're taking our angles as inputs for x and we're getting y values as outputs, and it ends up making exactly this graph right here. Okay, now this prompt right here, uh, what if the clock was larger? So what if I compare, let's say a clock whose radius is 2 feet to my clock with radius 1 foot. So now the blue one is the one that we started with, and this red one that I just made is the larger clock with radius 2. Let's keep graphing the y values of both and see how they compare. So as my angles, right, stay the same, my y value is a bit larger, right? I'm further out as I travel along this outside clock, this outside circle. The larger circle, we're further away, we're a higher y value, and it perfectly matches to this one right here, right? So as our angle increases, we're going to graph both of the circle's y values beside each other. And we're going to end up with something like this. Okay, so this is a lot like the sine function, right? We're hitting 0 at the exact same points, and we're hitting the highest point at the same time and the lowest point at the same time. But the difference, it's almost like I stretched my graph out. So notice here, normal sine only goes all the way up to 1, but this new red circle that's twice as big, that goes all the way up to an output of 2, right? And, oh, sorry, I meant to hide the code. I didn't want y'all to see that. Uh, is it not going to hide anymore? Okay, that's no problem. I just didn't want y'all to have to see all the horrible code that I wrote to get this to show up. Um, so we genuinely did just take our sine function and stretch it vertically. Now let me emphasize, we only stretched it vertically when we did this, right? This is all we're tracking. How did I get this? Well, all I really did was take my function sine of x and I multiplied it by 2, right? All of those outputs, all of those y values got doubled. So by increasing the radius, I'm just multiplying my sine function by that value. So let's say our radius was something like 2.5 instead. Well, now we'll do that exact same thing. How large, how far out does this function go? All the way up to 2.5 because my radius is 2.5. What if my radius is 3? Well, then the largest this goes is all the way up to 3, right? So this is if I had a larger shape, a larger circle, a larger radius, but I can just as well, instead of starting with something, right, bigger than 1, what if my radius ends up being smaller than 1? What if I was comparing this against a smaller clock? Uh, the weird thing that you can really see as I start tracing this out, it makes this into a square instead of a circle. Which is just the program trying to save some processing power. But yeah, that's pretty silly. regardless, the end result is we notice the y value for this smaller circle is going to be half as large, right? Because I made the radius 0.5. When we trace the shape all the way out, my red circle, my smaller circle, is only going to have this function graphed at half the height. So by increasing the radius, we make a larger function. By decreasing a radius, we made a smaller function with respect to y, right? Now, the next scenario, let's undo all this. What if some new gear that we tried to work on the mechanics of the clock, we replaced some gears around, and what if a new gear actually made our clock tick faster or slower? So let's say we somehow sped the clock up a little bit. If we increase our rotational speed by, let's say, 2, then what happens? So again, the blue is going to be our default here, and the red is going to be the modified version. So now, for the same amount of time has passed, right? The same x value that we're taking, our red circle, our red result is going twice as fast, right? So this blue part here, after the same amount of time, is half as big as the red angle that we're getting. And let's see if I can get it kind of close. Let me type it in. Pi over 2 pi, I mean, yeah, 2. Oh my gosh, we don't want to do that, I guess. Uh, yeah, we'll say 1.4. Okay. uh, yeah, we'll say about here. Um, when I moved about a quarter normally, if I'm if my other angle has gone twice as fast, then I will have already made halfway across my circle, right? So by this operation that I've kind of done, we can kind of see my function is happening twice as fast. I'm getting all the results that much quicker. Now they're going to end in the same place, but look over here, if I do it maybe like this, by the time the blue circle that's going the normal speed has only finished half of that sine movement, right? The red one has done one full period already, right? And let's say, again, compared all the way to the end, by the time our normal circle gets one full rotation, the one that's going twice as fast has gotten 2 rotations in. Now, this is something really, really interesting that I want to emphasize here. How do we compare the size of these? What's really happening here? Well, maybe we can kind of see it if I do this, but this blue arc that we get is getting squished all the way in here, right? The distance from 0 to pi is getting squished all the way into 0 to pi over 2, right? So by going twice as fast, I have compressed my function, right? I'm pushing it in like a spring. To go from the blue function to the red one, we're pressing inwards, right? Now, I lost my train of thought entirely. Sorry. So that's what happens when we made our function go faster, twice as fast, but what happens if we make our function go slower? So this is where we're at normally. But let's say my red clock only went half as fast. Let's say my rotational speed is just 0.5. Well, now, by the time that I normally would have completed one full period, I have only done half of the period. I've only gotten half of that full function's movement. So now, what was happening here at pi over 2 doesn't happen for the red function until pi, right? It takes us that much longer to get there. Imagine I ran half as fast as you did. Then after you ran 2 hours, I only made the progress that you made in 1 hour. Or I said that weird. If you ran for, it would take me twice as long to get to where you were, right? So it's taking this red function twice as long to get to where the blue function was. So at the end of this 2 pi for x, the red function has only gotten to where the blue function was at pi. And I'm just reiterating, I'm saying this so many different ways, but how can we write this inside of our sine function? Well, if we just normally have sine of x, then if I speed up the input by 3, well, I said 2 earlier, if I sped the input up by 2, if I'm going twice as fast, then that means on the inside of the function, I am multiplying my inputs by 2. So I get sine times 2x, and that's what gives us this image right here. The red function is the graph of sine of 2x. Now, on the other hand, this other example I just gave us where we had 0.5, then how do I represent this? Well, I'm going half as fast, so my inputs are getting halved, so I can write this as x over 2, or x times 1/2, x times 0.5, all different ways to do and say the exact same thing. I'm multiplying by 1/2, right? And so that is going to compress our function for larger numbers, but stretch the function out if we start going slower, right? It's just like if I said a football game was going really slow, it's dragging on. It feels like it's taking longer because things are happening so slow. It does take longer when things are moving slower, right? Okay. Now, what if instead of just looking at the movement of the hand itself, we wanted to see the actual position above the ground? Actual position above the ground is above. We wanted to see where its actual position is above the ground. Assume the clock is 6 feet in the air, high in the air. Okay, so normally, if all I care about, right, in these other examples, I treated the clock being right in neutral position as y being 0, right? Starting off just flat at 0. But in reality, our clock isn't really like sitting in the floor, right? In reality, our clock is 6 feet in the air. So let me have a second circle that I move up by 6 units. So this purple line is comparing the previous examples where I pretended the clock was just in the ground almost, to now my clock being 6 feet in the air up on the wall. Now, and this one does the weirdest thing as the angle changes. I don't know why it changes into the shapes that it does. Now as my angle increases, right, this one is just that much higher. Well, sorry, that much. What do I mean by that much? How much higher is it? it's staying 6 units apart. So as I increase my angle, my actual height is just 6 feet above where we were tracking it before, right? At this time, when that minute hand is all the way down, the center of the clock is 6 feet above the ground, but how far is the bottom of the clock from the ground? Just 5 feet, right? So now my angle traces all the way out and I make my full function. By just changing the height of my circle, all I really did was change the height of the function. By raising my circle up 6 feet, I just raised the function up by 6 units. So the blue is my normal sine function. I just took those outputs, I took the y values and just added 6 to them. Nothing really easy happening with this one, right? Um, we genuinely just moved the function up 6 units. So just do a +6 on the outside of everything. Um, so what if another clock started before the other is my last question. So normally this is the blue clock that we saw before, and again it traces its path out. But what if, and instead, I tweaked the clock trying to get it to start in the right spot, and I ended up with now the red one has a head start so that it's starting over here instead of in standard position. Well, now, after the same amount of time, it is almost ahead of the blue one, right? Once I go forward, right, this one has made more progress. This one is so much, whatever this value is, ahead of the other one. Now, this arc that I made with red, it's starting right where red started. So this is the same amount of time. This is the same angle between the red arc and the blue arc on the inside, but the actual height is that much further ahead. So once we trace our angle all the way through to pi, what do we get? Well, now both of them have made their full rotation, but like I said, this one was ahead of the other one. In fact, maybe I can get um, something like this, and we can see, hey, if I started ahead by about pi over 2, then I start at my peak, right at the top of the function, and then I go down and hit 0, and then I go back down to -1, back to 0, and back up to 1, right? So what really happened here, it's like I took all of these points and just shifted them. I just pushed them over, right? And how do I represent this inside the function? Well, if I started with just sine of x, if I started before the other one, then that's taking all the values I had and adding something to them. So if I started something like a quarter of a rotation ahead, well, a quarter of a rotation in radians is pi over 4, so that'd be my head start. And that makes me look like this. Well, notice the one that I have right now is pi over 2, so I guess I'll make this pi over 2. Now, notice something here, right? The peak that I get at the start with red happens over here with blue. So how do I move blue over to get it to sit on top of red? I move blue to the left because of this head start, right? And we should remember from our function notation, from our function work, that in algebra, sorry, our function transformation work from algebra, that adding on the inside of a function shifts it to the left. Something very unintuitive, but we'll look at a graph in a minute and we can see that maybe a bit more. But adding on the inside shifts our function to the left. Subtracting on the inside moves our function to the right. Okay, so how can we represent all of these transformations in function notation? Well, the first idea was by increasing my radius, I multiplied my sine function by something. Then I sped up sine by multiplying by some value on the inside. Then by considering my height, I lifted the function up, so I'd be adding on the outside. And lastly, I gave my example a head start. I gave the other circle a head start. So that also turned into doing some operation on the inside of the function, adding or subtracting by some value on the inside. So there's four kind of basic operations in math. There's these four basic things that we can do to our functions to do these transformations. Now, altogether, there's nothing stopping me from doing multiple at once, right? So what if I made the clock 3 times as big, but also pushed it down 7 units and gave it a head start of whatever, right? I could do that. Everything I said is kind of possible, right? We can do all of these at once. So we can do a times sine of b times x plus c plus some d, right? Where a, b, and c are just some random variables, right? We can do all of these at once, and they're going to have impacts on the function. So let me move over to Desmos here again, just our really fancy online graphing calculator thing. Let me, we have our sine function. Now we look at 2 times sine of x. Then again, we're seeing this function getting stretched vertically. And let's compare this to sine of 2x. This function is getting compressed horizontally. Now sine of x plus 2, our function was moved 2 units to the left, right? We have our peak over here, but now the peak is 2 units to the left all the way over here. And then by doing something like sine of x plus 3, that is probably the most simple. We just moved our function up by 3 units, right? So all of this together individually are kind of okay, but again, there's nothing stopping me from wrapping all of these inside of each other and saying something like 0.5 times sine of 3x minus 11, or let's do minus 2, right? So now the function is lowered, it is compressed, and it's shrunk down, right? The function starts at -2, goes up to -1.5, down to -2.5. So it's a smaller wave vertically. It's compressed in, it's a faster wave as well, and it's lower, right? We're doing all of these things to it simultaneously, these multiple function transformations all at once. Now something really kind of funny is happening, right? By doing an operation on the outside, right, 2 times sine of x, I have increased it, right? I made it larger. But if I do the same operation on the inside, instead of making it like kind of bigger horizontally, I have compressed it, right? So the operation that made it larger on the outside made it smaller when I did it on the inside. Vertically, we stretched by 2 units. Horizontally, we were compressed by 2 units. And compare that again to adding numbers on the outside. If I did sine plus 2 versus sine with plus 2 on the inside, right? This moved me 2 units to the left, whereas adding it on the outside moved us 2 units upwards. So very much multiplying and adding on the outside do exactly how we would expect them to. However, multiplying and adding on the inside have the reverse effect. So something that, there's some nuance here. Multiplying on the inside shrinks the function. Multiplying on the outside vertically stretches the function. Um, so yeah, there's some nuance, there's stuff to be careful about and everything, but there's also a lot of terminology that we should look at to describe what's happening here.